connected rates of change. Okay, so what connected rates of change actually means, right? Okay, it is, for example, if maybe there's a situation whereby they give you some y function, okay, related to some x square function, okay, something like that, okay, and there is certain meaning to y and x, okay, maybe for example the growth of the tree versus, and then it's related to how much water you pour in, okay, maybe it's something like that, okay. So for instance, it is this. So we want to find out what is the rate of the growth, okay, with respect to with relation to the rate of the water pouring. Okay, so if for example, if I want to find out the rate of the growth, dy over dt, okay, then will actually be, and then you only have the information of the x over dt. Okay, for example, the rate of the of you pouring water onto your plant. Okay, so in order for us to find out what is dy over dt, we will apply this. Okay, this process to actually find out what is the rate of my tree growing, okay, by finding out what is the derivative of the function, and then after that also given the rate of pouring the water, okay, something like that. Alright, so we will look first at try it. Okay, so example lah. Y is the growth height of the tree. Okay, then x is maybe amount of water. Okay, surely this equation doesn't work because it is quadratic, it doesn't make sense. Okay, so for example, right, if I want to find the rate of growth, okay, but I am given the rate of water given, okay, and since I know the relationship of the growth with the water, so I can differentiate it, okay, differentiate the function. Okay, the idea is something like that. Okay, maybe I give you a proper example. Okay, let's look at try it. Okay, so we have a curve that has this equation. And then we first want to find out what is the derivative. And then we want to find out what is the rate of change. Okay, so for instance, in this case, we are given this function. First find the derivative, and then in part 2, which is the concern in this particular unit, okay, we want to find the rate of change of y, right, when x is equals to 2 and when x is equals to 5.5, given that x is increasing at a constant rate of 2 units per second. Okay, so if x is actually increasing, we want to find how fast y will actually be increasing or decreasing. So we will first find out what is the derivative. We are using our product rule. So the derivative upon simplification, you will get 3x minus 4 over square root 2x plus 5. part 2, right, okay, what we want is the rate of change of y. So what this means is that we are trying to find dy over dt. Because we're looking at rate, that means it is over time, the change in time. So rate of change of y, so change of y over change of t. Okay, so rate of change of y will be dy over dt. So we want to find it for two different situations. When x is equals to 2, okay, that's case 1, and then after that, when x equals to 5.5, case 2. Okay, so they are expecting two answers. And then after they gave you the info that given that x is increasing, so if x is increasing, okay, that will mean that the value will have to be positive. That's what we covered yesterday. Okay, at a constant rate of 2 units per second. So since we're looking at the rate also, that means it is dx over dt, okay, will be equals to positive 2 since it is increasing. Okay, so we want to find dy over dt. We are given dx over dt, and we have already found out what is dy over dx. Okay, so into finding the answer, dy over dt will be equals to dy over dx times dx over dt. Okay, if you find that, if you notice, okay, this so-called equation itself or the formula itself, okay, it kind of satisfies some form of algebraic understanding. Okay, because algebraic fraction wise, although you are not supposed to see it as an algebraic fraction because it is just a notation, this notation does give you dx and dx if you cancel out dy over dt. So this is how the idea actually works. But please do not do your cancellation. Okay, it is just that the notation has been crafted and designed such that this understanding can occur. Okay. Yeah. Why what? Because you're looking at rate. Okay, rate of change of y. So change of y means dy, and then rate will be dt. Rate time what? Okay, over time. So change of y over change of time. Okay. dy over dx is what we have already done when we differentiate the function. You understand? Anybody else don't understand? Okay. Then after that, we are given over here dx over dt. So we will put in our dy over dx from part 1. Then after we multiply by dx over dt, which is 2. Okay, but since we want to first find out what is the value when x is equals to 2. So when x equals to 2, my dy over dt will be 3 times 2 minus 4 over square root 2x plus 5. Sorry, 2 times 2 plus 5 times 2. Okay. Then after that, your answer will be 2 over 3. Sorry, wait now. 1 and 1 over 3. Any questions up to here? Sorry? Answer correct. Okay, so the rate of change of y when x is equals to 2 will be 1 over 1/3 units per second. Yeah, so I'm going to do a second case now. So likewise, when x is equals to 5.5, the rate of change of y will be 3 times 5.5 minus 4 divided by square root 2 times 5.5 plus 5 times 2. And that will give you 6.25. questions? Do you all get an idea? You want me to do another example? Okay. Okay, maybe because I did not mention this before, right? The idea, okay, of dy over dx, we have previously understood that dy over dx refers to the gradient of tangent, right? Okay, I'm saying this regardless of the question. Okay, dy over dx is the gradient of tangent. But then we understand that for a straight line, tangent, okay, gradient is rise over run, right? Agree? Okay, which actually it is y1 minus y2, x2, x1 minus x2. This is the formula that we know. Okay, so it is actually the change in y, and this is the change in x. Okay, so another interpretation that you can understand from a derivative, this actually refers to the change in y, and this refers to the change in x. Okay, that's why in our question, okay, when we look at the rate of change of x, that's why this actually will refer that it is change in x. Rate means change in time. This is the idea of rate. So that's why rate of change of x would tell you that that is going to be dx over dt. You understand what I'm saying? Okay. So hopefully that this will give you a better idea over what are we trying to do and why is it that this process will actually work. Okay, so now moving into part C of question 1 in your exercise 15.4. Okay, we are given that the rate of change of x is 2 units per second, so dx over dt is 2 units per second. Okay, we want to find the rate of change of y at the given instant if my equation were to be y equals to x cubed plus 2. Okay, and we want to find it when y is equals to 10. Okay, so in order to do this, we know that in order to find dy over dt, we have to have dy over dx times dx over dt. We have dx over dt already, so now we need to know what is dy over dx. So dy over dx, differentiating the function given, you will get 3x squared. Okay, so dy over dt will be 3x squared times 2. But we want to find the value, okay, of this rate of change of y, and at a particular instance when y is equals to 10. But there is no y over here, so we need to know what is the x value. The corresponding x coordinate will be if you substitute y equals to 10 into the original equation. So x will be equals to 2. So when x is equals to 2, the dy over dt value will actually be 24. So therefore rate of change of y is 24 units per second. Alexis, are you okay?
Still can start when y equals 0.
Why you want to solve y equals to 0? The question give y equals to 10. Yeah. I didn't choose a random number. So, you understand?
Why do you get the well with the equal?
As in, never simplify it. As in, you can simplify it. My intention was to get an answer. Any questions? Okay, do you want to give it a try? Okay, could you do question 2A? Okay, so likewise, okay, wait. Okay, never mind, I think we do question 2A together.